can get messed up, right? Things that can kind of throw a wrench into the system. And the one we're going to talk about today is a thing called gate propagation delay. Right? And what that basically says is that when an input is applied to an output, or excuse me, when an input is applied to a logic gate, not an output, the output is not instantaneous. Right? Up till now, we've been doing this sort of like physics class, perfect spheres in a vacuum kind of thing, where when the signals change, right? Everything happens instantaneously. Well, obviously, it's not what happens in real life. When we actually build a physical thing, let's say that we have an inverter. We got X on the input, we got X prime on the output. What actually happens, and we model this with what we call a timing diagram. Timing diagram is going to be a big part of your life in this class for the rest of this semester. These timing diagrams are how we sort of simulate by hand the behavior of our logic circuits. And then of course we'll learn Verilog so that we can have the computer do it for us. So what we do is we sort of, the horizontal axis is time. In this course, we're going to predominantly use nanoseconds as our default unit of time, because that's just kind of where technology is right now. The vertical axis is going to be our logic level, but we're going to go ahead and post or plot on different signals, right? So that's X, we'll call that 0, we'll call that 1, we'll call that 0, we'll call that 1. And so what happens if, let's say, X is equal to 0, and then at some point in time we switch it over to 1, right? We flip the switch. Up till now, again, like I said, we've been assuming it was instantaneous. It was ideal, but that's not what happens in real life. What happens in real life is it sort of kind of curves up and then curves over. Just like that. And then the signal stays at 1 forever. And on the X prime, so if we started, if the universe begins with X is equal to 0, X prime starts equal to 1, right? Now, this takes time to charge up, right? Because transistors or capacitors and all that fun analog circuit stuff causes this to take some delay. Well, there's really not a point. It's not until like about here that the output goes, oh yeah, we have switched to 1. And then it itself sort of ramps off down to 0. And so we qualify or quantify the time that it takes from when we sort of hit go on the transition to when the transition actually was completed. This time is called the propagation delay. So it's the time from when we actually switch the input to when the output actually occurs. Occasionally I teach a course called Testing of Digital Systems, where we use actual lab equipment like multimeters and oscilloscopes to characterize these values and measure like at what voltage level will the transition actually occur, and measure the propagation delay and stuff like that is one of the things we do in that class.
I have a question.
Hey, what's up?
How did the word when the line is experiment?
I just drew it. It's arbitrary, yeah. Don't worry, I'm not going to ask you to do that. That would be that depends wildly on the actual semiconductor characteristics of the transistors. If you take advanced digital systems design, you can talk about that kind of stuff.
So this graph right here is basically like the electricity going through the gate, and then that just shows like the.
Exactly, right? We can say, we don't usually label the vertical axis, but you could also kind of think of it as the voltage on the circuit, right? 0 volts to
5.
5 volts is what's commonly used, right? It would absolutely translate over that. Although like in modern stuff, it's like 0 to like 1.
So that's what that propagation delay is it actually going through that gate?
Yep.
That's cool.
Yeah, so it's the time it takes to actually do the thing. And this diagram is called a timing diagram. I'll get rid of that now. All right, so let's work through a really simple example of a timing diagram for a really simple circuit. So let's say that we've got a circuit that consists of an AND gate that has just a 1 on one of the inputs, an input that we'll call A on the other one, and it feeds into an OR gate that has a 0 there, and the output goes to F. And we'll say that we're going to look at the case when A goes from 0 to 1, and all gates have a propagation delay of, let's call it 20 nanoseconds. Now this is often not true. In fact, always it's not true. All gates have different propagation delays. That's one of the things we talked about was NAND gates. NAND gates traditionally have a much shorter propagation delay than AND gates and OR gates. But here we'll kind of simplify things and say all gates have a propagation delay of just 20 nanoseconds. So let's go ahead and set it up. Let's have this, give us some room, F over there. We'll put F down here. There's our 0 and our 1. Next up, I'll do this gate, which is, we'll just label it as gate 1. And then A, we'll put up here at the top. And we'll mark out some ticks. We'll do 10 nanosecond steps. 10, 20, 30, 40, 50, 60, 70, 80, right? Time in nanoseconds. Okay. So first thing is we're going to look at A as it transitions from 0 to 1, and then from 1 back to 0. So what I want to do is this. Let's leave A at 0 for 20 nanoseconds, and then let's take it to 1. And for these diagrams, we are going to forget about the curve business. We're going to draw them just as straight lines for this. And let's say that it stays 1 until it hits 60 nanoseconds, and then it goes back to 0 and it stays at 0 for the rest of our simulation time. So if A is 0 in the beginning and the other input is 1, the output of our AND gate, gate 1, is going to be what in the beginning?
Can you repeat that?
At the beginning of our simulation, what is the output of the AND gate? A is equal to 0, the other input is 1. So what's the output of the gate? 0. Good. So it stays at 0. Now when A transitions from 0 to 1, the output of gate 1 is now going to be, input is 1, 1, so the output of gate 1 is going to be 1. But the catch is, there's a propagation delay, 20 nanoseconds, which means that that transition for gate 1 won't occur until 40 nanoseconds. And then it's going to keep going until this transition comes down, and it's going to be 20 nanoseconds after that. So it's not going to be until this 80 nanosecond mark. And it goes back to 0. So notice how the output pulse sort of lags behind the corresponding input pulse. That's the important bit. Now, if we take a look at the OR gate, or excuse me, the output of the OR gate, our actual output function f, it's ordered with 0. So we had 0 and 0 all the way until at least here. And then we had 0 and 1, which means that the OR gate output becomes 1. But again, this is going to wait until 60 nanoseconds to click up to 1. And it's going to stay, actually 80, 90, if we call that 100 out there. It stays at 1 until G1 comes back to 0, and then it's 0 or 0, but there's still 20 nanoseconds of delay before it comes back to 1. So there at the very end, will it drop back down to 1. So there's two important things that, oh yeah, what you got?
Couldn't you use the not exclusive OR gate or the equality gate to find out the time delay? Because isn't it it's the exclusive OR but the not version? How do you say it? What's that one?
The XNOR?
Yeah, the XNOR.
Yeah.
The XNOR, couldn't you use that to find out how long the time delay is?
Yeah, except then you
Or
run into that kind
circuit?
of quantum mechanics problem. Well, that gate has its own propagation delay, right? It has its own effect on the circuit and stuff like that. So
That is true.
you kind of can't use gates to measure other gates, right?
That's right.
So yeah, but the important thing here is there are two things to note, which is from the moment, so notice that all of the outputs sort of lag behind each other. And then here for the circuit as a whole, we switched it at 20 nanoseconds, but we didn't actually get our effect that we were looking for until 60 nanoseconds. There was a 40 nanosecond lag between when we hit it with the input and we got our corresponding output. Now 40 nanoseconds might not seem a long time, but if you're not seem like a long time, but if you're designing a processor or a GPU or something that runs at 3 gigahertz, 40 nanoseconds is a long time, right? So it matters at the high speeds of modern digital systems. 40 nanoseconds is a lifetime. A lot of stuff can happen in 40 nanoseconds. Okay, so the important take home is for you guys, we can look at this, we can know what our propagation delay is, and we can draw the timing diagram. Yeah? Cool. All right. How much time do we have? A little bit of time. Okay. So, this business of propagation delay can lead to some unexpected consequences.
Why did we have to move out the other class?
What's that?
Why did we have to move out the other class?
Because I like chalkboards more than I like writing on my tablet, and I was tired of the thing breaking in the middle of the class every time. Yeah.
Prefer a chalkboard?
Yeah, I love the chalkboard, man. You get all like dusty, like you walk, like it feels like scholarly to like work on a chalkboard. Man. You work on a chalkboard, you walk away, you feel like you did something, and you're covered in the dust.
All right, you can tell the truth. You just want, when we're not paying attention, you just want to rub your nails against the chalkboard. That's the real reason why you want it.
Yeah, I've never been able to do that.
Yeah, I've never had long enough nails to do
Yeah,
that.
I've never had long enough fingernails to make it
Like,
work. Yeah. I like the, like I said, I don't know, it feels old and scholarly. I like it. It's more satisfying than writing and tablet.
I couldn't do it back in the element.
What's that?
I just prefer the whiteboard over the chalkboard.
I prefer a board over the tablet for sure, right? But if given the choice between the dry erase board and the chalkboard, man, you gotta go with the chalkboard. It's classic. That's what our forefathers did, you know? All right, let's do more, because we don't have a lot of time. We actually have some stuff we're gonna go through. A little bit more of a sophisticated example of a circuit. So we're gonna have an input that we're gonna label it as B. We're gonna feed it actually through an inverter. It's going to go through an AND gate to A, and another AND gate. This is going to take B, and another output C, and then we're going to feed it through the OR gate, and we're going to get our output F. So this is a two-level and/or circuit. Don't forget it's two-level because remember we ignore, for the purposes of quantifying everything, we kind of ignore the presence of the inverter. Although here it's going to kind of lead to some interesting results. So this is a working logic circuit. It's got a whole truth table. We're going to focus on one specific set of minterms, right? We're going to focus on the transition from, let's see, 1, 1, 1. To 1, 0. We're going to drill down on that. So what that means is we're going to start our timing diagram with A. Actually, we're going to leave A equals C is equal to 1. And we're going to take B from 1 to 0. And the last thing to note is that the propagation delay for all gates, here let's make it 10 nanoseconds. So let's draw our time diagram. So it's T in nanoseconds. And those are 10 nanosecond steps. And let's see, we'll have F, and then we'll do each of these logic gates individually. Let's call it, in fact, let's just use their Boolean expressions. So this one is B and C. This one is A and B prime. And then let's just have B. Okay, so A and C are equal to 1, they're locked in. B starts at 1 and then is going to go to 0. So let's say that B starts up here at 1 until the 20 nanosecond mark, and then it goes to 0, and then it just stays at 0. Right? We're only concerned with just that one transition. So let's look now at the first gate, A and B prime, right? It started with what? If A was equal to 1, so we had 1 there, and B was equal to 1, that means we had a 0 here. So the gate AB prime started its life in this simulation at 0, right? That sure is like the most hilarious sweep.
I'm so sorry.
All right. So A and B prime starts at 0. Now, when B transitions to 0, right, that goes to 0, makes that 1, which means it's 1, 1, which means AB prime is going to switch from 0 to 1. But when is the switch going to happen?
After 10.
What's that?
After 10 nanoseconds.
After 10 nanoseconds?
After the 20. So it's going to start at 30.
Yeah, so it starts at 30. Well, not at 30, because the transition here starts at 20, right? But remember, we got two gates here.
Oh.
The inverter. We got paid 10 nanoseconds for the inverter, and then the output of the AND gate is another 10 nanoseconds, which means it's going to be, for this gate, its transition won't occur until another 20 nanoseconds down the line. So it's not until 40 nanoseconds that it switches from 0 to 1, but of course it's going to stay at 1 forever. Next up, let's look at B and C. Now B is going to, so C is equal to 1, that's an AND gate. So it starts off its life where? With 1 and 1, right? So the AND gate BC starts at 1, and then when its B transitions to 0, it's going to go to 0 because it's going to have 0 and 1. But its transition will occur at 30 nanoseconds, right? Because B switched over at 20 nanoseconds. This AND gate doesn't have to wait for the inverter, right? Because it's tied to B. So it's going to switch 10 nanoseconds later, which means its transition from 1 to 0 will occur here at 30 nanoseconds. Everybody with me so far? Let me check. No, it's working. Sorry guys on Discord, they're talking about it can't not being able to hear very well. Everything seems to be working on my end though. Sorry about that, guys. Okay. All right. So BC switched over at 30 nanoseconds. Is everybody with me? Why that happened? All right. So it's going to switch before AB prime does because AB prime is of course dependent upon that inverter. Now let's look at F. So F is equal to what? A, B prime, or BC, right? Which means that if A is 1, we started with B is 1, that means B prime is 0, or 1, and 1 means that we get 0, 1, or 1, right? So it's going to start off at 1. Until stuff happens. Okay, so B going to 1. Well, let's see what happens. Okay, so at this point right here, where are we at? A, B prime is equal to 0, but BC is equal to 1, right? So we have 0 or 1. But it's not until this point right here where BC transitions to 0 that here we're going to get 0 or 0, right? Yeah.
What? So the bottom number, I mean the bottom dash represents 0 and the top dash represents a 1.
Yeah.
Okay, cool.
0, 1. 0, 1, 1, 0, 1. For each guy. Yeah. So at this point, when BC transitions to 0, the output is going to be equal to 0, right? But it's not going to happen until 10 nanoseconds later, right? So it's going to go to 0. But at the same time it went to 0, A, B prime went to 1, so then we had 1 and 0 again. Which means 10 nanoseconds later it's going to go back to 1. And then it's going to stay there forever.
So each 10 nanoseconds it switches from 0 to 1.
Well, just in this case, that's what I'm saying. So here,
Yeah.
when we had a 1 and 1, or 1s on A and C, but we went B equals 1, B equals 0, right? In both cases, F should be equal to 1, right? So by all of the rules that we've talked about so far, should F have ever changed? No, right? Because we started with a thing that should be F equals 1, and we ended with a thing that equals F equals 1, right? But here, because of the topology of the circuit and the way that it works out, for a brief moment, the circuit itself switched to 0. And then went back to 1.
Problem?
Is that a problem? The answer to that question is, that depends wildly on, well, what are we doing? What is F attached to, right? if, this causes like a weird rounding error in your calculator, it's probably okay, right? If this causes, the missile to explode while it's still attached to the airplane, then that's probably bad, right? And you want to deal with that, right? But then it becomes sort of a philosophical, do we need to avoid the logic hazards, right? So this thing happening right here is called a logic hazard. A logic hazard is when, due to the topology of the circuit and the interaction between the delays, an unexpected or an unwanted change in the signal occurs.
So for this circuit, how would you get rid of that logic? Would you have to take out the,
Come to the right place, man. We're going to talk about it in just a second. Well, actually, we might talk about it
take out the
one day.
NOR?
What's that?
Would you just take out the NOR?
There's no NOR. What are you talking about?
Take out the NOR, then the not for these?
We can't do that because we got to keep the circuit. We're going to get there.
Okay.
We're going to get there. And it's pretty cool, the answer. Again, we are probably going to talk about it on Monday. So, but let's finish this up with a little bit of terminology. So, there are two types of logic hazards. There's what's called a static hazard. And a static hazard is when the unwanted bit only occurs once, when the error only happens one time during the transition. So, for example, if we are at 1 and we go to 0, so that was 1, that's 0, that's 1, where we should have been 1, but we momentarily went to 0 and then came back, and that only happened once. That's called a static 1 hazard. Because it should have been static at 1, but it wasn't, right? On the flip side, if it's at 0 and then goes to 1 and then stays at 0, 0, 1, 0, that's called a static 0 hazard. If, for example, the hazard occurs more than once, so for example, we get something that's like it's at 1 and it went to 0, and then it came back to 1 and went back to 0, and then stayed on. If it happens more than once, then it's called a dynamic hazard. Dynamic hazards are bad. If a dynamic hazard occurs, you get rid of it. If the static hazard occurs, it's up for debate.
What I was trying to ask was, so propagation delays, so let's say the propagation delay is 20, so every 20 nanoseconds it goes from 0 to 1 or 1 to 0, is that how that works?
Only if the input signals change. Right, so these only occurred in response, so everything was the same, and we had B was equal to 1, but we changed to B equals 0, right? And because the signal takes time to propagate through the logic gates, every time your signal hits a gate, you got to stop and wait 10 nanoseconds before you can move on to the next one, right? So because of how that comes out, the final answer that we wanted here doesn't appear right away. The system has to trickle through the system until you get the final output. And again, what we care about right now is that it can lead to these hazards, these places where your system can give an unintended output because of the relationship with the timing. Cool? All right. In that case, we are out of time for today. We will talk about how to detect and remove logic hazards from our designs on Monday. So, thanks so much. If there's nothing else, have a good weekend. Be safe. Yeah, I'll post so I still have like my notes on my tablet. Even though I'm using the chalkboard here, I'll still post the notes I'll post my copies of the notes on OneNote. So, cool. All right. Thanks, guys.
Have a great day.
You too.